All right, number 11 says, use the table below to answer the following questions. And we've got some different ionic species here with their reduced form, oxidized form, and the names of the different ions there. So complete and balance the following equations. All right, so the permanganate ion reacting with iron 2 plus. Okay, so the first thing, we've got our permanganate ion, and we can see that the redox pair for the permanganate is the manganese ion. Okay, so we're going to get the permanganate going to manganese. Okay, the second reaction that we're going to have is our iron 2 plus, and that's going to our iron 3 plus. Okay, here's the redox pairs here. Okay, so we need to balance these half equations here. So the first thing we need to do is make sure that our metals are balanced. We've got one manganese on this side, one manganese on this side, done. Okay, we've got some oxygen on the left side of the reaction, so we need to balance for oxygens. And the way we balance for oxygens in these half equations is to add water. So we need to add 4 water molecules on this side. Okay, now we've got 4 oxygen atoms. We've got 4 oxygen atoms on the right hand side as well. Now we've got some hydrogens now over here on the right hand side, so we need to add some hydrogen ions or protons to the left hand side. Now we've got 8 over this side, so we need to add 8 protons. Okay, now all of our elements are balanced. We need to balance for charge. So over this side we've got -1 plus 8, which gives us a total of +7. On this side here we have a +2. Okay, so we need to balance charge by adding electrons. So therefore we need to add charge to the left hand side because we want to make that come down to the same charge as the right hand side. Okay, so to get +7 to +2 we need to add a negative charge of 5, so we're going to add 5 electrons to the left hand side. Okay, and that is our balanced half equation there. Now what we're going to do is we have to balance the bottom half equation. So in this case, first check is yes, we've balanced all our elements. We've got the iron and the iron. We don't have any oxygen or hydrogen, so we don't need to worry about balancing for those. We just need to balance for charge now. Okay, the higher number is on the right hand side. So that is the side we're going to add our electrons to. We only need 1 electron so that both sides now have a +2 charge. Okay, now we can go down and write the full equation for the reaction. So to be able to write the full equation, what we need to do is have the number of electrons on both sides of the equation equal. So we can see here with our top half equation, we've got 5 electrons involved. With our bottom half equation, we only have 1. So what we actually have to do is multiply this whole bottom equation by 5. Okay, and then we can write out our full equation here. Okay. So what we're going to end up with, so let's write out, we're going to have 5 iron 2 plus, going to 5 iron 3 plus 5 electrons. Okay, so let's work this out. The electrons cancel out on both sides. Okay, and that's all we can cancel out because we don't have any other water or hydrogen. So now we can write the full equation. We're going to have 1 permanganate plus 8 hydrogens plus 5 Fe2 plus forms our manganese plus 4H2O plus 5 Fe3 plus. Okay, so you can see here to get this full equation, I've just added everything up that I've got left in both of my half equations. So I've got these and this on the left hand side, okay, and I've got these plus this on the right hand side. Okay, so the exact same process that we have to follow for this next one here. Again, we write our half equations out. So we've got our bromide ions. So you might want to have this table handy up the top still so you can see the bromide ions. So the bromide ions are going to go to Br2. Okay, and the dichromate ions, Cr2O7 2 minus, is going to go to chromium. Okay, actually says acidified, so that gives us a clue there's going to be some acid involved, but we should actually see that when we balance these half equations anyway. So let's balance the bromine first. First, we've got to balance for the number of atoms of that element. We've got 2 bromines on the right-hand side, so we need to balance on the left-hand side. All right, now we need a balance for charge, okay? In this case, what we've got is a 2 negative charge on this side. Okay, remember we can only balance charge by adding electrons. So what we're going to have to do is add 2 electrons to the other side of that half equation there. Okay, now the second half equation. All right, so we've got chromium and chromium. We need 2 chromiums on this side to balance those out. Now we've also got oxygen involved. So we've got 7 oxygens on the left-hand side here. So we also need to add 7 oxygens by adding water on the right-hand side. Now we need a balance for hydrogens. We've got 14 hydrogens on the right-hand side. So we need to add 14 hydrogens on the left-hand side. Okay, this is good because this, remember, our protons are our acid, and it said that the dichromate ions were acidified. Okay, so we can see here we've got our acid present. All right, now we need a balance for charge. So on the right-hand side, we've got a total of a 6 plus charge from these chromate ions. On the left-hand side, we've got a 2 negative plus 14, which equals plus 12. Okay, so remember we need to add electrons to the side that has the highest positive number. So that's going to be our left-hand side, and we need to add 6 electrons to bring that down to the same charge on both sides. Okay, so I'm going to get rid of these. Now to write our full equation, what we need to do is make sure we've got the same number of electrons on both sides of our equation. We can see here that we've got 6 on the left-hand side with our bottom half equation. We've only got 2 on the right for our other half equation. So to balance that up, we're going to need to multiply this whole top equation by 3, which is going to give us a total of 6 bromide ions forming 3 bromine and 6 electrons. Okay, so now our electrons are going to cancel out. So the full equation that we're left with is going to be our 6 Br minus plus our dichromate plus our acid, which is great because we've been told that it's in acidic conditions, and that's forming 3 bromine plus 2 chromate plus 7 water molecules. And there's our balanced full equation for that question there. All right, next question says, use the metal reactivity series provided to answer the questions below. So if you guys were given a question like this, you'd be obviously given the metal reactivity series so that you can use that. So the first question is, using an equation to illustrate, if applicable, predict what would happen if a magnesium ribbon is dropped into copper sulfate solution. Okay, so we're going to start magnesium. We've got a solid magnesium plus copper sulfate solution. Now, on our metal reactivity series, we need to look at which metal is more reactive. Remembering that the more reactive metal wants to be in solution more, so it wants to be the ionic species. Okay, so in this case, we actually see that magnesium is the more reactive metal. So magnesium is actually going to want to be in solution more than the copper, so it's going to displace the copper, and the magnesium is going to form ions. So if this is the case, what we're going to end up with is magnesium sulfate in solution, and we're going to get some of that copper solid crushing out of solution. Okay, next one is copper solid plus zinc chloride. Okay, so in this case, what we see on our metal reactivity series is that zinc is actually more reactive than copper. That means zinc wants to stay in its ionic form. Okay, so the copper solid is not going to displace the zinc in ionic form. So there's actually not going to be any reaction here occurring at all. They'll just stay as a copper solid and a zinc chloride solution. Okay, so next we're starting to look at our galvanic cells. All right. So it's possible to produce an electric current from an apparatus similar to that shown below. So we're looking at our galvanic cell. Okay, so we might call it a galvanic or voltaic cell. Either is fine. Okay. So the next part of the question says, name part X and describe its composition. So part X on the diagram is here. Hopefully you guys recognize that this is a salt bridge. And it will contain some sort of filter paper soaked in salt. Salt solution. Okay, you might like to give an example. For example, potassium chloride is a common one that we use. All right, the next part of the question says, on the diagram, clearly label the anode, cathode, direction of electron flow, and the positive electrode here. Okay, so when we're looking at this, we need to look at which one of these is going to be the most reactive. And what we see when we do that is magnesium is the most reactive. So the magnesium metal, okay, is going to be forming more of the magnesium 2 plus, okay? Therefore, the electrons are going to be produced at this electrode here, okay? The electrons are going to then flow in this direction down to the copper electrode. So we'd label that with our electron flow, okay? Because our electrons are being produced over here, this is going to be our negative electrode, which is our anode. Okay, our copper is going to be our positive electrode. That's because what will be happening here is we'll be getting our copper 2 plus combining with these electrons. Okay, so the copper 2 plus will be combining with the electrons to form solid copper here at this electrode. So our positive electrode is our cathode. Okay, what else did we get asked to label? Anode, cathode, direction of electron flow, and the positive electrode, which is our cathode. Okay, so we've described and labelled everything on that diagram. All right, so now we've been asked to write our half equations. All right. Oops, we've got a typo here. So write a half equation to show what's happening. This should be copper electrode. So what's happening at the copper electrode? Like we said, we've got our copper 2 plus ions in solution. They're combining with the electrons that are coming down through the electrode to form solid copper. Okay, done. Next one says write half equation to show what's happening at the magnesium electrode. So we said because magnesium was the more reactive metal, the solid magnesium is going to form our magnesium ions and is going to produce electrons when it forms those ions as well. So that's the half equation occurring at that electrode there. All right, so last question here. we have a zinc air battery that's powered by oxidizing high purity zinc using oxygen from the air. These batteries have a high energy density and are relatively inexpensive to manufacture. All right, the equation for the reactions that occur at each electrode are given below. Okay, so they're given below here, the bottom of the diagram. All right, so we want to identify the half equation for the reaction that occurs at the anode. All right. And if we look at the question here, the question actually tells us the answer to this one here, okay? So it says, all you're asked to do is identify the half equation for the reaction that occurs at the anode. And it actually says here, if we read carefully, the zinc powder anode, okay? So the zinc powder is this here. So that is going to be the reaction that's occurring at the anode, okay? So all we have to do is copy down that half equation, and that is the one that's occurring at the anode. Actually gives us all the information right there. We just have to read the question properly. Okay. So next question says write an overall equation for the cell reaction. So first we need to look at the electrons that we have here. We've got 2 electrons in this half equation, we've got 4 in this half equation. So we're going to need to multiply this top half equation by 2, which gives us, let's rewrite over here what we're going to end up with. We're going to end up with 2 zinc plus 4 hydroxide forms 2 zinc oxide plus, zinc oxide plus 2 H2O plus 4 electrons. All right, then what we're going to get is our electrons in both cases cancelling out. What we're left with is 2 zinc plus 4 hydroxide plus oxygen plus 2 H2O. And we've got our 2 zinc oxide plus 2 H2O plus 4 hydroxides. All right, what we've actually got in this case here is we've got some more things that we can cancel out in this reaction, in this equation here. All right, so we can actually see we've got hydroxide species on both sides of the reaction here, and we actually have the same number of hydroxide species, okay? So those hydroxides are just going to cancel straight out, okay? They're gone. We've also got water on both sides of the equation. We've actually got 2 lots of water on both sides of the reaction, so they also cancel out. So what we're left with here in our equation is 2 zinc plus the oxygen is forming 2 zinc oxide. That's it. That's the overall reaction that's happening in this battery. Okay. Third part says state the energy change that occurs in this type of cell. Okay, so in this type of cell, remember it's a spontaneous reaction that's occurring. So we've got our chemical energy from those differences in reactivity being converted to electrical energy. Okay, and last part here, it says in the zinc air button cell, the zinc is present in powdered form. Explain the choice of this powdered state. Okay, so in this case, the zinc, so the option here would be to have zinc in powdered form or zinc in a solid strip form, okay, because we want a metal of some form. The reason they use powdered form is that when we've got anything as a powder, we've got that broken up into much smaller particles. So the zinc has a larger surface area area in powder form. Powder form. Therefore, faster reaction rate. Okay, so we know that when we increase surface area, we're going to have a faster rate of reaction. Therefore, that's why we use the zinc powder rather than a solid strip of zinc. And that's it for this practice test.